Hello and welcome to another video. Today we are going to check out the two previous videos that I made, but we're gonna combine them all in one. So it's gonna be combined Couette and Poiseuille flow. So let's do that. Alright, combined Couette and Poiseuille flow. So what we basically derived from the last video from the Poiseuille flow was that, well, from the force balance on a very small fluid element like this, so delta x and then delta y, and we had the pressure forces as well. I'm going to write up the Taylor expansion for this one just so we can save a bit of time. And then we had shear like this, which this was tau, and then when we go one step up in the vertical direction, we can approximate this using a Taylor expansion, which becomes tau plus d tau dy delta y. And then when we did the sum of the forces in the x direction should be 0, then we get that, well, the net pressure gradient forces, that should be equal the net shear forces, right? And then I know I did a little oopsie in the last one, but what it basically should be, and I'm gonna correct myself now, is that when we do all of this, we get, when we do the pressure forces, we have P delta x delta y plus or minus, because it's a net force, the net force delta x delta y plus dp dx delta x delta y. That should be, and then the net shear forces, tau delta x delta y minus tau delta x delta y plus our change in tau along y, like that. And then these terms cancels because they are similar, they are the same, and then dx dy also cancels, so we end up with what we should have gotten the last time. Dp dx is equal to d tau dy, and then we substitute in the Newton's law of viscosity, which was tau is equal to mu du dy. And then what we get here is that we have dp dx is equal to mu du squared dy squared, right? And then we had our boundary conditions. But now I'm going to draw up the two cases. So now we have both, we have Couette, which we established in the in some videos before, that we have this sort of scenario where our top wall is moving with the velocity v. So then our velocity profile is a linear function, and this is without the pressure gradient. It's just the shear that is dragging the fluid elements along the top wall, making it move, right? So this was Couette flow. And then we have Poiseuille flow, And this was a flow, typically a flow inside a pipe. And remember that all of these flows are laminar, so it means that they are happening at a relatively low Reynolds numbers. And this could, for example, be, let's say that we have, this channel is very, very small, and we have, for example, honey that is being dragged along this plate, and it moves very, very slowly. And, well, laminar means that the streamlines are, well, they are nice and organized on top of each other. They don't mix. There is no turbulence. So this is laminar cases for both of them. Laminar, steady state, and fully developed. So back to our Poiseuille flow. Well, this was a typical flow between two parallel plates, and then it's a pressure difference driven flow. So we have something that looks like this, right? So for a combined Couette and Poiseuille flow, what this basically is that we just combine the Couette and the Poiseuille flow. So then what we get, we still have our second order ODE equation, and our boundary conditions. Those are still kind of the same at the bottom one. So u of y is equal to 0. Let's see that both of this is arbitrary height h, like this, right? U of y equal to 0. Well, both of the velocities are 0. So that is one boundary condition. And then we have u of y is equal to h. When we combine these two, the velocity at the top at h should be the same as that plate moving. So that should be v. So then if we integrate this, we still end up with an equation for how this works. And then if we remember the equation for the velocity profile for the Couette flow, it was u of y is equal to vy over h, like this. This was for the Couette flow. So we valued at 0, this becomes 0 as the no slip. When this is h, well, those two terms cancelled and we end up with the velocity v. And with this one, well, we have that u of y is equal to 1 over 2 mu dp dx, and then we had y, and then we had y minus h. So this also satisfies our boundary conditions at this certain point. At here at y equals to 0, at y equal to 0, the velocity should be 0. So if we plug in all of this, well, this term goes to 0, and then that's multiplied with this, so everything goes to 0. At h, it should also be 0, because when we put h here, this term becomes 0, and then all of this becomes 0. So all of these are valid solutions, and they are, well, they're telling how the velocity profile looks like. So what we do is, well, we know this second order ODE, and if we integrate this twice with respect to y, we get a generic solution with some integration constants, and then we can plug in those two boundary conditions, and then we get the velocity profile of a combined Couette and Poiseuille flow. Or we could do it much more simple, and we use what is called the superposition principle. So the superposition principle, that is just a linear addition between this one and this one, right? So then what we get is, we say that u of y, and we call this combined because it's combined Couette and Poiseuille flow. Well, it's just a linear addition between those two, so we just add them up. So then we have 1 2 mu dp dx y minus h, like this, plus our Couette solution, which was v times y over h. So this is our solution for the combined velocity profile. And what is the point of this, you may ask? Well, it is to get a better understanding of how the pressure gradient works. So now I'm gonna need to make some more space. So let's do that. I'm gonna remove this ones. Like that. Right. So let's keep going with our example. So now we're gonna sketch this up. You could do this by simply inserting values into y and see how the velocity component u of y varies with respect to y. But what we are gonna do is, well, we already know how it's gonna look like, but I'm gonna draw how it looks like when we vary our pressure gradient term dp dx. So what we have our channel like this. So let's say in our first example we say that dp dx is equal to 0. So dp dx, which is our pressure gradient is equal to 0. So that means that P1 is equal to P2, meaning that there is no pressure difference, which also should imply that, well, the whole of this term, our Poiseuille velocity profile term, all of this cancels and we are left with our Couette flow. So then what this then becomes is just our linear velocity profile, our Couette flow. Simply like that. So then it's just a shear driven flow and there's no pressure gradient force acting. But then let's say that we have a favorable pressure gradient. You can call this number 2. We say that dp dx is less than 0, so this would imply a favorable pressure gradient, which means that P1 is bigger than P2, and by reference, this is P2, this is P1, right? So then when we set the pressure gradient, that is a favorable pressure gradient, so we have a big value here and a smaller value here, meaning that the flow is pushed from left to right. Well, we get a solution that, okay, looking something like this, we always have to fulfill this top boundary condition. So it should always be v at the top of the wall, and we see that this blue line meets our velocity v here, but we also have to accommodate for the no slip at the bottom here, which should be 0. So then we have something looking like this. Right? And then we could do another one. Let's see. We can do a yellow one. Well, we can do number 3. What happens if we make this pressure gradient even larger? Meaning that we have an even higher value for P1 and an even less value for P2. So dP dx is much smaller than 0, which is still a favorable pressure gradient case, but now P1 is much bigger than P2. Well, what happens? Yeah, the thing is that we push more fluid through the pipe, so the velocity profile has to expand to the right because we're pushing more fluid, and you can say the average velocity increases. So then it has to go like this. So we see that when we are making a more and more powerful favorable pressure gradient, we are basically pushing more fluid through the section, and we're also bending this velocity profile to the right. So that is one case with a favorable pressure gradient. And now, if we take another color, we can do green, light green. Number 4. Maybe it's a bit hard to see the difference between these two colors, but I hope it will be fine. Now let's see. We have gone through a 0 pressure gradient. I should write this here, that this is a 0 pressure gradient case. This one, when the pressure gradient is equal to 0, we call that a set PG. 0 pressure gradient, and we have a favorable pressure gradient when the gradient is less than 0. But now, well, what happens if dP dx is bigger than 0? Well, then we have something called an APG, or an adverse pressure gradient. And then that implies that, okay, if dP dx is bigger than 0, that means that P2 is bigger than P1, meaning that we actually have flipped around the pressure difference. Now we are trying to push fluid this way. And then what happens then is that, well, our velocity profile is looking like this. So now we are still moving this way, but we are working against what would be the Couette flow. So now the velocity profile is tending to the left. Or sorry, these arrows are not correct. It still goes like this. But now we see how it's tilted inwards with the adverse pressure gradient instead of being bent to the right with the favorable pressure gradient. Okay, so now we should also see what happens if dP dx is much bigger than 0. So let's do that. Let's try to find a fitting color for this one as well. Let's see if I can get, if I do have any more colors. I don't know if I have that, but we will. I have a purple here, that would be fine. Okay, so now the 5th case. dP dx is much bigger than 0. This is still an APG, or an adverse pressure gradient. So this means now that P2 is much bigger than P1, meaning that now we have even more pressure forces working against our Couette flow, which at some point when this is getting a value that is at some value bigger than 0, well, we are getting something that looks like this. So now we actually have some kind of backflow at this section, this small section here. Here we still have a flow in the from left to right, but this small section here we have a flow in the opposite direction, which brings us into a very nice a topic that should be understood, which is flow separation. Well, what is flow separation? Flow separation is when the flow detaches from the surface, and we have a good understanding of this and a good law when you can tell when the flow is separating. Well, we say that the flow is separating when the shear force at the wall becomes 0, or very close to 0 at least. And we know that from Newton's law of viscosity that tau is mu du dy, which we can simplify and say that, well, mu is a constant. So we say that mu, or tau, our shear stress at the wall, that's proportional to our velocity gradient near the wall. So du dy at y goes to 0. So we can draw the velocity gradient would be this. That's one velocity gradient. So here is the change of y, and here is the change of u. Yeah. We can approximate this derivative by simply asserting this into this. So the more the slope, the more the velocity profile tilts downwards, the more shear we have, because this is a steeper gradient than this, which means that this case, number 3, well, we have a pretty big shear stress at the wall. Comparing to this blue one, where we said that we have a favorable pressure gradient, but it's smaller than 0, well, we have a velocity gradient there as well, but that one is not as steep as this one. So that means that the blue one, where dp dx is less than 0, that has some shear stress, but it doesn't have as much when we increase the pressure gradient. So when we increase the pressure gradient to a favorable pressure gradient, we push more fluid through the pipe or the section, but it comes at a cost that the velocity profile has a steeper gradient near the wall, which means more friction, more losses. So that's something you have to accommodate for. And let's look at when we have an adverse pressure gradient, case 4 and 5. Well, we see that, oh, this gradient here, that is looking almost 90 degrees. So that is on the very verge of having no shear stress. When this comes close to tilting perpendicular or vertical like this, then we have no shear stress. That means that there is no, you could say, force that is holding our velocity profile connected to the surface, which means that it's going to slip or it's going to separate. So even this case, when we have dp dx is larger than 0, we see that, well, given this value, that it is on the verge of separating. And this purple case, when we have a very big adverse pressure gradient, well, we definitely have flow separation because we have backflow. So yeah, this is like a visual representation of how you could see flow separation, how you actually know if your flow is separated or not. And this trend goes into a pretty big thing. We have something called the total drag. We say that the total drag which is basically when we have a flow over, for example, a cylinder. We do like this. So this is our cylinder, right? Here we have a uniform flow coming onto our cylinder. Now this is viscous flows, it's not inviscid, so there is gonna be some viscous effects. And when this happens, well, it's gonna separate at some angle or at some point on the flow or on the cylinder, because we have an adverse pressure gradient. So if we draw like this, we say that this is a adverse pressure gradient and this is a favorable pressure gradient. And what you could basically say here is that, well, a favorable pressure gradient is when the streamlines are squeezed together, which means that the flow is accelerating. And that is basically because if we use continuity, we say that, well, at our area 1 and then at our area 2, if we set up a small control volume around this cylinder, we say that, well, continuity, mass flow 1 should be mass flow 2. And we know that mass flow is rho u a. So we know that when there is an area increasement, the pressure increases, but the velocity goes down, right? And when we are entering this stage of the cylinder, well, we can see that the area here is getting smaller and smaller and smaller because we're coming closer to the cylinder, which means that the flow is accelerating because the area is going down. So when the effective area that the flow sees when area is going up, well, the velocity has to go down, but the pressure is increasing. When area is going down, well, U has to increase and the pressure has to decrease. So the flow is coming in here, it's accelerating, and that is what the favorable pressure gradient is. It's accelerating the fluid, we have more shear against the wall, and then at a certain point, well, we can see that there is an area increasement over here at some certain point on the cylinder. And well, then we have a bigger pressure difference, which means that the pressure is working in the opposite way, just like these two cases. And then at some certain point along here, we will have no shear stress because the pressure force is acting in the opposite way, pushing the flow upstream rather than downstream. So this is also a visualization of how all of this works, favorable and adverse pressure gradient. But back to our total drag. Well, our total drag is skin drag plus what we call form drag. And this is due to separation. or what is caused by APG, an adverse pressure gradient. And this is, well, proportional to our gradient, du dy, the shear stress. But the thing about this is that form drag is having a higher order, or a magnitude, you could say. This term is dominating very often. So the thing is that when we increase the pressure gradient, yeah, we have more shear, but the thing is that when we have more shear, it's going to be more resistance against flow separation, which means that our form drag is going to be a smaller contribution than if we were to have a smaller favorable pressure gradient, because then the flow would separate earlier and we would have more form drag. So yeah, I hope this makes sense. It was a visualization and some key points on favorable pressure gradient, adverse pressure gradient, and the combined Couette and Poiseuille flow, which does visualize this fairly well, I would see. And you could say that having a favorable pressure gradient comes at an expense. You're pushing more fluid through the pipe, which means that you will get a fuller velocity profile, which have a bigger slope at the wall, more shear. But what is positive from having more shear is that you get less form drag, because you have more resistance against adverse pressure gradients. So yeah, I hope you guys enjoy that, and I will see you guys in the next video. Thank you.